Hello everyone, my name is Vaibhav. I'm a second year PhD student at Georgia Tech, and today I'll be talking about my work on characterization of route variability in LEO satellite networks. I'm certain most of you would have heard about these satellites, especially with Starlink launching over 3,000 satellites in the past few years, with more than 10,000 of them being planned for the next decade. These satellites have shown their ability to provide high bandwidth and low cost internet access in rural and disaster affected areas such as Ukraine, Iran, Florida, and Australia. Further, a lot of recent work has shown the potential of these satellites to outperform the current terrestrial networks. A key reason for that is the ability of these satellites to form a network using the inter-satellite links or the ISLs, through which they route the data to reach the destination ground station. Before getting into more details, I'll briefly provide a primer on LEO satellite networks. Every satellite consists of 4 laser links to be used as the inter-satellite links. These links are connected in a plus grid ISL topology. I'll explain this using the satellite in the center of this figure. This satellite connects to its neighbors in the same orbit using the yellow-colored intra-orbit ISLs, while it connects to its neighbors in the adjacent orbits using the purple-colored inter-orbit ISLs. In these networks, paths are made up of 2 ground satellite links or the GSLs and 0 or more ISLs depending on the distance between the source and destination. For example, in this path here between New York and London, you can see there are 2 GSLs and 3 ISLs. These networks have a highly dynamic infrastructure where satellites can move at speeds of about 27,000 kilometers per hour. This results in a satellite being accessible for a maximum of 4.5 minutes. So, how does this impact current networking algorithms? Fundamentally, networking algorithms assume stable paths and RTTs. For example, congestion control and adaptive video streaming exploit this stability to aggressively try to converge to the capacity of the selected path. Similarly, traffic engineering algorithms assume a stable ranking of paths to perform functions such as load balancing. Now, as I just mentioned, these networks have a very high level of dynamism, so some variability is to be expected. However, the scale of this variability would determine whether current networking algorithms can be used as is in these networks. Therefore, to answer this question, in this work, we look at the extent of variability in LEO satellite networks to ascertain if this variability is small enough so that current networking algorithms can handle that, or if the variability is high, which might require modification to the current algorithms. I'll first talk about our objectives for this study. We first look at route churn, which we define as the measure of the frequency of change in routes between a source-destination pair. I'll give you a spoiler here that there is a lot of route churn. So we try to see if this route churn results in any significant gains. That is this route churn necessary? Next, we look at RTT variability, which we define as the measure of the RTT variation between a source-destination pair. As you can imagine, there is a lot of RTT variability, so we try to see if this variability can be explained. Next, I'll briefly talk about a simulation methodology. In this work, we simulate the Starlink, Kuiper, and Telesat constellations based on their publicly available FCC filings. However, for this talk, I'll just focus on the first shell of the Starlink constellation, consisting of 1,584 satellites at an orbit of 550 kilometers. For all our experiments, we use the satellite path models to predict the precise satellite locations at given timestamps using the publicly available configurations. For our work, we use the shortest path routing algorithm to minimize the RTT between the source and destination. We are able to do so by calculating path length using the positions of the ground stations and satellites while using speed of light propagation. I would also like you to note here that we do not perform a complete packet level simulation, but we are just looking at propagation delay. We measure route characteristics for a total of 100 minutes while recomputing routes every second. For our workload, we look at the 100 most populous cities as ground stations resulting in about 5,000 source destination pairs. These 5,000 pairs for a total of 100 minutes result in nearly 600,000 routes being observed. I would like to repeat here that all these routes were the shortest ones at some point during these 100 minutes. So now let's get into the more interesting parts. The first thing is how much route churn is observed. For this, we look at all the 600,000 paths that I just talked about. We plot a CDF of their usage times and their lifetimes. Let's look here at what happens at the 1 minute mark. You can see that while more than 80% of the paths exist for more than a minute, just about 30% of them are being used for the same duration. This implies that paths are being used for far lower time compared to their existence. There are two main reasons for route churn in LEO satellite networks. The first one is the path ceasing to exist, or the other one being rerouting between valid paths for reasons such as lower latency. To ascertain the reasons for route churn, we plotted another CDF. Here, we look at the ratio between the path lifetime to the path usage time. On the left side of the CDF, you can see that about 25% paths are being used for their entire lifetime. This means that in these cases, route churn occurs because of the path ceasing to exist. However, on the other side, you can see that more than 50% paths are used for less than half their lifetime, which means that in these cases, route churn occurred because of the existence of another smaller path. Now, you can say that this route churn makes sense if the gains provided by here are significant. This is what we try to see if these gains are significant or not. That is this route churn necessary? We start this discussion by using Jakarta-Bogota as an example. Here I show you all the paths being used during a 200-second interval. The dotted line represents all the individual paths, the solid line represents the actual RTT selected, and the diamonds show the path switches. You can see here that there are a lot of path switches that occur, some of them because of the path ceasing to exist, like the three ones at the bottom, or in a lot of other cases, because of the existence of another shorter path. Nothing exemplifies the latter than the second and third switch that you see here. The first switch is fairly obvious because the first path ceases to exist, making the routing algorithm jump to the blue path. However, a few seconds later, the red path becomes shorter than the blue one, making the routing algorithm switch to the red path. Only for the routing algorithm to switch back to the blue path just a few seconds later after the red path ceases to exist. Another few seconds after that, the routing algorithm switches to another path because of the presence of another shorter path. I'm sure most of you would agree with me here that at least two of these switches were unnecessary, especially after I tell you that the latency gain here was just 5 microseconds, which is 5 orders of magnitude lower than the RTT here. Having looked at this example, we try to see the general case for all the 5,000 source destination pairs if the latency gains show any other patterns. We plot a CDF of the ratio between the minimum RTT and maximum RTT observed during the 100-minute simulation duration. Here we observe that more than 80% of the paths are abandoned for less than 25% gain. This means that in most cases, route churn results in very minimal latency gains. It's not just latency. As we show in the paper, this unnecessary churn can impact application performance significantly. Having looked at route churn, we next look at RTT variability. We study the extent of RTT variability by plotting heat maps from a fixed source point to 2,700 uniformly spaced points all over the globe. For the heat maps, we use the metric of the ratio between the maximum RTT to the minimum RTT over the 100-minute duration. As you can see, in most cases, variability is fairly small. However, there are some cases where variability can be as high as 2.5 times. We observe similar patterns for other points such as Darfur in Sudan and Kiev in Ukraine. In addition to the magnitude of variability, we also observe that this variability exhibits a spatial structure. So we tried to see if this variability can be explained. In the paper, we perform a thorough analysis of the path components, which help us provide justifications for this variability. However, for the talk, I'll just provide you a couple of interesting case studies to provide some intuition. First, I'll present to you the Darfur-Isangi route where I show you 3 paths over a period of 6 seconds. The first path consists of 3 satellite hops, the second one has 2, while the third one is a single hop. This leads to the first path being 2.5 times longer than the third one. Now, I'll quickly warn you here that even though these paths, the first path doesn't seem as long compared to the third one, this is because these are 2D representations of 3D paths. However, the key thing I would like you to take away from this example is that for shorter routes, RTT variability can be highest because of high chances of changes in path composition. Having looked at the shorter paths, let's see what happens for slightly longer ones. Here, I present to you the Kiev-Cairo route where I show you 2 paths. The first path has 3 satellite hops or 2 intersatellite links, while the second one has 3 intersatellite links. Even then, the second path is shorter than the first one because of the type of links used to compose this path. Essentially, the point I'm trying to make here is that for satellite networks, hop count is not a good proxy for path length. Having looked at these intuitions, let's revisit this heat map. The ring-like structure in the middle here represents very short paths. However, as you keep moving away, variability creeps in because of the changes in the links that are being used. In the paper, we also look at an approach that can help decrease variability. However, in the interest of time, I would like to conclude my talk here and would encourage you to take a look at that in the paper. I would like to summarize my talk with the main learnings that we had. The first thing we looked at was how much route churn exists and whether that can lead to any significant gains. We saw that there is a lot of route churn, which in most cases does not result in any significant gains. Next looked at how much RTT variability exists and if this can be explained. We saw that RTT can change by up to 2.5 times while exhibiting a spatial structure. Finally, I would like to thank my co-authors and sponsors for this work. I look forward to your comments and questions at my email address here. Thank you.